All right, we're working on intermediate algebra, section 2.4. If you're following along in your book, that starts on page 82. All right, the topic is solving systems of equations using substitution. So this is the third method we're going to learn for solving a system of equations, substitution. The first example has a system that says 7x plus 3y equals 4, 7/3 x plus y equals negative 5. And if you remember from the last section, which was elimination, for elimination, we want our equations in standard form, ax plus by equals c. But in substitution, we want to solve one of our equations for one of the variables, or in other words, isolate one of the variables. It doesn't matter. You can look at these equations. There are 4 choices here. It doesn't matter which one you decide to isolate, but usually one of them is easier than the others. In other words, if you isolate the variable that has a coefficient of 1, there will be no division involved. If you try to isolate this x, you're going to have to divide everything by 7, causing fractions. If you try to isolate this y, you'll have to divide everything by 3, again causing fractions. Here, you're going to have to multiply times a reciprocal, causing fractions. Here, no division is involved in isolating this y. So if you have a variable with a coefficient of 1, it will be the easiest one to isolate. So we're going to carry that equation down, and we're going to isolate this y. Because it has a coefficient of 1, it's the easiest one to isolate. To isolate this y, we just need to subtract this x term. So subtracting 7/3 x will bring it to this side as a negative 7/3 x. These now cancel, and we have y equals negative 7/3 x minus 5. And this is important because for substitution, you want to take that expression that is equal to your variable that you isolated and put it into the other equation instead of that variable. So what I'm going to do is I'm going to take this expression that's equal to y, and I'm going to substitute it here instead of y. That's why we call it substitution. So again, just to reiterate, it doesn't matter which variable you isolate. You can choose any of these. Once you isolate that variable, you take the expression that's equal to the variable or on the other side of the equation, and you put it in the other equation instead of that same variable. So when I carry this down, let's see if I can scroll this over a little bit. There we go. We'll start with this equation, 7x plus 3y equals 4. And again, I want to put this value of y in here instead of this. So 7x plus 3 times negative 7/3 x minus 5 equals 4. And I hope you can see the whole point of that now is that we only have one variable. We only have x, and the y is now gone. So we're going to simplify all of this and solve for x. The first step here is distribute this 3. So that turns into 7x plus, don't freak out because these are fractions, this is really 3/1, and these 3's cancel. So this would be negative 7x. And I'm going to erase this plus sign because we don't need, I guess I'm not going to erase it. We don't need 2 signs there. So that plus sign is gone. When we distribute this 3 times negative 5, we get negative 15 equals 4. If you're looking closely at what's happening here, you got a positive 7x and a negative 7x, and those x's actually cancel off. We end up with a statement that says negative 15 equals 4. If you remember from our previous couple lessons, when this happens, when you're trying to solve a system of linear equations, if both the variables cancel off, which is what happened here, we have no variable, and you have a false statement, this means there are no solutions. If you end with a false statement, there's no solution. and that means the lines are parallel. They never cross. So there's no solution. The lines are parallel for this system. For example 2 is on page 83. We're solving using substitution. We have negative 9x plus y equals 1. 8y equals 72x plus 8. And again, for substitution, you want to have one of your variables isolated. It doesn't matter when you look at this that it's not in standard form. This first equation is, but it doesn't matter. You don't need your equations in standard form for substitution. You just need to have a variable isolated. Now this one has a coefficient of 1. This would be easy to isolate just by subtracting or adding the 9x to move to the other side, or this one would be easy to isolate just by dividing off this 8. If you're going to do some division like this, I would first check to make sure, are you going to end up with fractions here when you divide by 8? And it's really nice that you don't, because both of these are divisible by 8. So the division's not a big deal. If these did turn out to be some fractions, it would have been easier to deal with this one instead. So the object, of course, is to avoid the fractions. So we're going to start with 8y equals 72x plus 8. To isolate this y, divide off the 8, we end up with y equals 9x plus 1. And now we're going to take this statement that's equal to y and we're going to put it in the other equation instead of y. So that's going to happen over here, starting with negative 9x plus y equals 1. I need to put this in here, so negative 9x plus 9x plus 1 equals 1. When you look at this now, again, you can see the x's eliminating again, like on the last example. That doesn't always happen, by the way. And we're left with a statement that says 1 equals 1. Unlike the last example, this is a true statement. Whenever this happens and your variables cancel each other off and you're left with a true statement, this now means there are an infinite number of solutions, or infinitely many solutions. And why? Because these are the same line, or the lines lie on top of each other, or the lines coincide, or something to indicate that the lines are actually in the same position on a graph. All right, example 3, still on page 83, says solve using substitution. Negative 5x plus 3y equals negative 12. X plus 7y equals 10. With substitution, your first step is to isolate one of the variables. So we're looking here to see which one will be easiest to isolate. And of course, with a coefficient of 1, this x will be the easiest one to isolate. So let's carry that down here. X plus 7y equals 10. To isolate x, this 7y will need to go to the other side. Of course, when we move it to the other side, the sign changes. So x equals negative 7y plus 10, or you could write it as 10 minus 7y. It doesn't matter. They mean the same thing. And then we're going to take this expression, which is equal to x, and put it in the other equation instead of x. So it's going to go there. So we're going to write this over here to the side, starting with negative 5x plus 3y equals negative 12. We're going to put this in here for x because it's equal to x. Use a parentheses. Negative 7y plus 10 plus 3y equals negative 12. Now just a matter of simplifying all this. So distribute, combine like terms, and all of that stuff. So what are we going to end up with here? 35y minus 50 plus 3y equals negative 12. 35y plus 3y is 38y. So 38y minus 50 equals negative 12. We're going to add 50. Still trying to isolate y here. So we have 38y equals 38. So of course when you divide by 38, you're going to have y equals 1. All right, so different from the other two examples, the first two, we did not get our y to cancel off here. So if you actually do all of this and you get a value for x or y, that means that there is one solution. There's one solution. The lines intersect at, and this is the y coordinate for the ordered pair telling you where the lines intersect. We just don't have the x coordinate yet. So we'll take what we know about y and we'll plug it into one of these equations. Actually, this one is going to be the easiest one to plug it into because it's already defining what x is equal to. So you can plug y right in here and find out what x equals. So that's what we're going to do. I'm going to carry that down here. Let's scroll up a little bit. Maybe, no. Guess I can't scroll up. X equals negative 7y plus 10. Y equals 1, so we'll put a 1 in there. Negative 7 times 1 plus 10 is negative 7 plus 10, so x equals 3. And that will be your x coordinate for your ordered pair here. So this is your solution. There's one solution. The lines intersect at the point 3, 1. All right, example 4 is on page 84. It says solve using substitution. Negative 5x plus 3y equals 55. 7x plus y equals 1. With substitution, you need to isolate one of your variables as the first step. So looking at these, this y right here is going to be the easiest one to isolate because it has a coefficient of 1. So we're going to bring that equation down and isolate y. 7x plus y equals 1. To isolate this y, 7x going to the other side. So y equals negative 7x plus 1. Then we'll take this value, this expression that's equal to y, and we'll put it in the other equation instead of y. Now I have seen students take this expression and put it back into the first, it's the same equation that they started with. You can't do that. If you take this expression and you put it in here, you're comparing the same equation with itself, and you'll always get infinite solution because you're comparing the same two equations. If you start with this equation, solve for a variable, you have to substitute into the other equation that you haven't used yet. So we'll put that equation over here. Negative 5x plus 3y equals 55. We'll take our expression that's equal to y and we'll put it right in there. So negative 5x plus 3 times negative 7x plus 1 equals 5. Then we're going to distribute, combine like terms, and solve. It looks like we're going to be solving for x here. So once I distribute, I have negative 5x, don't like that, minus 21x plus 3 equals 5. And I just got that by distributing. 3 times negative 7 is negative 21. 3 times 1 is 3. These two terms are like terms, so we put them together as negative 26x plus 3 equals 5. Subtract the 3. We get negative 26x equals 2. And I'm just realizing right now that I wrote this all incorrectly. I don't know if you guys caught it at the top. This should be a 55 here. So in this 5, I'm just going to go back and I'm going to make this 5 into 55. This should not be a big deal. It changes that this 2 should not be a 2. It should be a 52. All right, that makes a lot more sense. I'm sorry I made that mistake. I hope that didn't confuse anyone. All right. So now we need to divide by negative 26, and we end up with x equals negative 2. All right, after you do all of this substitution stuff, if you get a value for one of the variables, again, that means there's one solution. That the lines intersect at one point, and that point has an x-coordinate of negative 2. Next, you need to find the y-coordinate for that one point. So we need a y-coordinate here. You just need to take your x, substitute it in one of these equations. I'm going to use this one that tells me what y is equal to, and I'm just going to substitute x in there. It would be great if I could scroll up a little bit. Y equals negative 7x plus 1. I got that from here. I'm going to substitute my x value in right there. So y equals negative 7 times negative 2 plus 1, or 14 plus 1. So y equals 15. And that will be the y value for your ordered pair solution. So this right here in green, this is your solution. There's one solution. The lines intersect at the point negative 2, 15. All right, example 5 is on page 85. Solve using substitution. 2x plus 3y equals 9. 5x plus 4y equals 5. All right, when you're using substitution, you have to isolate one of the variables. The easiest variable to isolate is the one that has a coefficient of 1. However, none of these variables have a coefficient of 1. So now we can't avoid the fractions, but we can be smart about which variable we isolate and how many fractions it gives us. So we'll think about this. If we want to isolate this x, we will have to divide everything by 2. When I divide by 2 here, fraction. When I divide by 2 here, another fraction. So 2 fractions if I divide by 2. But if I isolate this y, I have to divide by 3. This will be a fraction, but this number, 9, is already divisible by 3, so no fraction here. This will be a whole number. So isolating this y is preferable to isolating this x because it gives us fewer fractions. If I look down here at the second equation, I can say the same thing. If I divide by 5, a fraction here, but this is divisible by 5, so no fraction. So isolating this x gives us 1 fraction, but isolating this y, divide by 4 fraction, divide by 4 fraction, this will give me 2 fractions. So it'll be preferable to either isolate this y or this x. Doesn't matter which one you decide. I think I'm probably going to go with the top and isolate y. I will tell you, this is different from the way your author did this in the book, because your author chose to isolate this x, which yielded 2 fractions. I think that that's not the wisest move, so I'm going to isolate this y, and I'm going to carry it over here to the side. I'm going to have 2x plus 3y equals 9. To isolate this y, 2x goes to the other side. We change the sign when we do that. So 3y equals negative 2x plus 9. And then we divide off this 3. So we end up with y equals negative 2/3 x plus 3. I think it's way wiser for you, unless you're super great with fractions, to try to cut down the number of fractions as much as you can. So now this is equal to y. So now I'm going to take it into the other equation instead of y. I'm going to put it right there. So let's pull this equation down. 5x plus 4y equals 5. We're going to take this expression that's equal to y. We're going to put it in right here instead of y. So that's going to be 5x plus 4, use a parentheses, times negative 2/3 x plus 3 equals 5. Now I know that you guys are all freaking out about this, but you have to be able to do this. If you need some help with fractions, if you're not that great, I have other videos on this YouTube channel that just deal with fractions in the developmental playlists. You can find all kinds of videos for fractions. So we're going to distribute this 4. So that's going to give us 5x plus, all right, what is 4 times negative 2/3? Right now I'm going to erase this plus sign because that will be negative, won't it? This is 4 over 1. If you envision it as 4 over 1, it's 4 times 2 on the top, 1 times 3 on the bottom, or 8/3 x. And then 4 times 3 is 12. Now, combining like terms, for starters, these are like terms here. They're both x terms. This 12 needs to go over here and join the 5. So that's the first thing I'm going to do. I'm going to put this negative 12 over here to join the 5. That makes negative 7. And then I'm going to deal with these fractions right here. All right, these fractions are different signs, so you're not going to add them. You're going to subtract them and take the sign of the larger one. But to do that, they both need the same denominator. So let's maybe draw a line over here, and we'll do it over here. 5 converts to 15 over 3. So I have 15 over 3x minus 8 over 3x. So the 15 over 3 is obviously larger, so the sign here is going to be a positive sign. So we'll have a positive sign when we're done here. 15 minus 8 is 7, so this turns into 7 over 3x. Now, still trying to isolate this x here, we need to multiply this fraction times its reciprocal, which is 3 over 7. Same thing to both sides. So we're going to multiply this times 3 over 7. I'm going to put a 1 under there. These all cancel just to make x. Over here, the 7's cancel, and I end up with negative 3. So that's part of my solution, x equals negative 3. So already I can tell that there's one solution. That means the lines intersect at the point that has negative 3 for its x-coordinate, and we need to find a y-coordinate. Rats, I scrolled up too far. Where are my equations? Here they are. So you can use any of these equations. This one has y already isolated, and y, since I'm trying to find y, but this one has no fractions, so maybe we should use that one instead. So let's pull that equation down here. Let's use blue. 2x plus 3y equals 9, and that's from one of our original equations right there. We've already found that x equals negative 3, so we're going to scroll up, and we're going to substitute that negative 3 for x right in there. So 2 times negative 3 plus 3y equals 9. 2 times negative 3 is negative 6. Add the 6 to both sides. We have 3y equals 15. Divide by 3, you get y equals 5. So that's the y-coordinate for your solution now. So there's one solution. The lines intersect at the point negative 3, 5. Okay, so I'm going to cut this here. The word problems are going to be on the next video.